Okay. I have a few announcements. Nigel, are you going to show me the participation sheet? Okay, thank you. All right. So some of you are doing extremely well, and the extra points that you're getting beyond the 15 participation points might come in handy if you need a push from an B- to a B or an A- to an A. I would look at how much you participated, so that might help. Some of you are not talking at all. These are 30 points and they're easy points. You can ask a question, you can add in a clarification, and it's okay to ask any questions because in my books, no question is a dumb question. Every question is valid. I don't want you to be embarrassed. Maybe somebody else wanted to ask the question, and then if you ask it, other people will benefit. So I really would like to encourage that. It's not really about the grade as much as, at being involved in the class discussion. So some of you just, are very shy. Try to come out of your shy zone. Nobody's gonna judge you. Thank you. And if you notice, if you have a wrong answer, I don't tell you wrong, and I don't frown at you. It's okay. I don't expect you to know the answers. It's okay to have a wrong answer. Okay, the other point I have is one of you asked me if we can have an extra credit full lab report. So what does that mean? Like if we have an assignment that is partial lab report and you want to just gain extra credit, you can submit the full lab report for AA or MS or moisture lab. The way we're going to grade it is graded like we would grade a full lab report, but the partial lab report is 20 points, full lab report is 30 points. So we'll grade it out of 30, but when we enter the grade, if you get 25 or 28, it would be 8 additional points. It will be out of 20. Instead of out of 30. You don't have to do it. I don't look mad. So this is somebody that one of you asked. We don't expect you to do it. You don't have to do it. We don't want you to do it because it's additional grading. But somebody asked and I'm obliged to give the answer. But you don't have to do it. There's a lot of opportunity in this class to get extra credit. It's not the only opportunity. Nobody's going to get better treatment in any case. So I'm just answering one of your fellow students' questions. No, nothing to worry about or be upset about. You're not required to submit any full lab report for partial report. Okay, because I see some of your faces going down and I don't want you to feel bad about it.
So if you do want to do that for extra credit, instead of putting the short lab report as your cover page, put the long lab report as your cover page. And that will indicate to me that you want me to grade that for your extra credit 10 points possibly.
Yeah. So again, this is option for you if you want to use it.
Would the due dates still be the same? So like if it's a partial lab report, it's due 5 days after lab, but if you choose to do a full lab report, it's still due 5 days after lab.
Question. No, we can be lenient. If you need more time, we can be lenient with that. Okay. And Drew.
Would you have to do all of the full? Like let's say if you just wanted to do like do the discussion on the abstract, just
No, don't get us into this.
Okay,
Don't
okay.
get creative.
Okay.
We're already doing something that we've never done
It's
before.
either all or none.
It's either or not.
Exactly. Is it just for this one, correct? Like SRAA or MS one?
No, anyone in the future that is partial you want to pick, you can. Allery,
If you did a full lab report in like
got points deducted, is there any chance that we could end up like hurting ourselves by doing a full lab report? Like,
No, you will not get less than 20 on your full lab
okay,
report.
so yeah, I feel like-
Anything above 20 points is going to be extra credit.
Okay.
It's going to be extra. You're not going to hurt yourself. Again, this is another opportunity for potential extra credit. I'm sure you don't need it. There's a lot of extra credit potential. But like I said, it's my obligation to answer to one student request. Okay, Matt.
So when will like the rest of our extra credit go? Like grade book and not to the end of the semester?
At the end of the semester, you see, before you go into the final, you see all your points, including extra credit. Yeah, you can count them yourself every time you give me a sheet of paper, that's +2.
Okay.
Right? But then we count them at the end of the semester, and there's a grade for extra credit that go in one column rather than have multiple columns for extra credit. Yeah,
Where is like extra credit added? Because I like different points from different things, different percentages,
extra credit added in the book.
like the grade book.
The grade book, there is a column for extra credit.
Okay.
You'll see that entered before your final. You'll see an extra credit column that will include actually the +10 that I would give it one day to everybody in the class.
Are we allowed to see the sheet to like see where we're at with participation?
Yeah, well, you can ask Nigel, there's no secret, you can see where you are. If you reached your point, that doesn't mean stop talking. Keep your interaction, I would appreciate that. Okay, the other thing, I have a couple of other announcements. I'll be traveling on Friday after lecture, actually literally going to the airport. And I will be gone Monday and Wednesday, but you don't have free time. You're still going to go to lab and you're still going to come here for lecture. We have guest lecture, Samira in the back. She's going to lecture on Monday and Sirab is going to lecture on Wednesday. So wonderful postdocs, and you will hopefully enjoy the lecture. Now, last thing, midterm. The midterm is supposed to be not this Friday, next Friday. How do you feel about postponing it to Monday? So instead of Friday, the 5th, would be Monday, the 8th. Who doesn't want that? Raise your hand. Okay, we'll have it on Friday. Even if it's one person, it's originally scheduled for Friday. If one person doesn't want to move it, we won't move it because it's originally on your syllabus and calendar on Friday. So it will be it. All right. No hard feelings, you guys. Don't shame those people that didn't want to move. Okay. All right. Why am I not seeing what I want to see? Okay, now share. I don't know, doesn't want to. Would it work if I do this? I don't know why it's doing that. Oh, why is it doing that? I'm not able to change the slides. Except if I'm here. Oh. Fine. All right. This not cooperating with me, technology. All right, so UV vis spectroscopy is our, this is the last lecture that would be included in your midterm. There is infrared as part of spectroscopy. I will cover that when I come back. So for now, we cover UV vis, and that would be the last lecture. Everything from the beginning to this lecture will be included in the midterm. Okay, so let's see what you remember and what you know. Molar extinction coefficient is constant for all analytes. A highly concentrated sample may result in deviation from Beer's law. Incident beam minus exiting beam is equal to the light absorbed by the analyte. Okay, so there's certain terms here that I just want to know if you remember what they are. What's molar extinction? Does anybody remember what this means? Okay, never mind. It's another word for it is absorptivity, and it is really very specific to the analyte. And I'll show you Beer's law equation so that you see what absorptivity is related to. It's really unique for every compound. It has to do with in which wavelengths that compound absorb light. Okay, so absorptivity, I'll show you why it's called sometimes molar extinction later on. A high concentrated sample may result in deviation from Beer's law. Let's remember, what's Beer's law? Any idea what Beer's law is?
Isn't it like absorbance of the concentration?
It is the relationship, the linear relationship between absorption and concentration. So Beer's law, Beer's Lambert, actually, there is two people that came up with the law, but I don't know why Lambert got dropped off the name, but mostly it's referred to as Beer's law, and it should be B with a capital B, sorry, not the beer that you drink. Okay, so Beer's law states that there is a linear relationship between absorption and concentration. And when you have really high concentration of molecules in your sample, there will be a lot of interaction between these molecules. So when their molecules are interacting, their absorptivity differs. Then you would have not the correct absorption. Then you will lose linearity between absorption and concentration. That's why when we're measuring absorption or fluorescence, we have to be within a certain range of concentration, not too concentrated, so that Beer's law is obeyed, so that you have this linear relationship. Because above certain concentration for particular analytes, the relationship won't be linear. It will curve and plateau. So we need to dilute our samples in a way that you don't have a lot of interaction between the molecules. Incident beam, what is incident beam? That means the light that is hitting your sample. Minus exiting beam, when the light hits the sample, you have some absorption happening, and then the light exiting that reaches the detector, okay? Because some light is absorbed, and then the light reaches the detector. So do you think this is correct? No. No, it's not correct. So it's not direct subtraction of incident beam and exiting beam or transmitted light, because you have potentially, you have scattered light, you have reflected light. When the light hits the cuvette, some light gets reflected. In the sample, you have large molecule, might scatter light. So you might have light scattering, light reflection, you might have some fluorescence happening. So no, whatever light is exiting is not equal to the light, actually absorption is not equal light incident beam minus exit. So we'll talk about that some more. So this is, none of this is correct, basically. Yes, Michael?
Part of C, is that when you're stressing that the incident beam comes out because some gets fluoresced or whatever, the exit beam is always going to be longer?
No, no, no.
That's not the same.
No, this is not the fluorescence. The exit beam is not fluorescence with longer wavelength. It's
Yeah.
because the compounds are going to absorb some light, but light is also not going to be absorbed by the molecule. Light is going to continue. Not all the light is going to be absorbed by your molecule.
Oh.
Right? Because the molecule is not going to absorb all of the light that is hitting. So it will absorb at a particular wavelength, and then some other photons of light are going to continue pass through your sample and not be absorbed or scattered or reflected. Yeah, so not all the light that hits the sample gets absorbed.
I have a question. You just said like they were all false, but I thought you just said that B was true.
Oh,
I was just making sure.
I stand corrected. So yes, my dear, B is correct.
Thank you. I was like,
I'm glad you said that. I'm glad that you said something. See, even I can get misleading.
We were right.
Yeah. When I explained it, I explained correctly, but then I told you none of the above, because I'm used to confused students and none of the above. So B is correct. Good catch. Okay. In both absorption and fluorescence spectroscopy, UV vis radiation is used. The transmitted beam is the signal measured. A grating monochromator is needed. Just give it us logic, what your logic would tell you. Sometimes, yes, Ryan. A is correct. So UV vis is where you have absorption and fluorescence happening. IR, you get absorption. So keep that in mind too. But this is correct. And then what about B and C? Can you? B is correct as well, because the light absorbed is not the light that is going to reach the detector. The light that is reaching the detector to do the calculations for absorption is actually the transmitted light. Okay, a grating monochromator is needed. Is it? So what is a monochromator? Do you remember? Kayan?
Just a sample
Multiple samples. No, let's dissect the mono and chrome. Valerie?
It's just, it emits a single frequency wavelength.
Yes, so the grating diffracts the light into multiple wavelengths, and the monochromator selects one of these wavelengths to get onto your sample. So this is needed if we're doing quantification. So if we're doing identification type of work, this is not needed. Okay, but for quantification and Beer's law and relating absorption to concentration, we have to have a singular wavelength. All right, so in some cases this is correct, in some cases it's not correct, yes.
For fluorescence, we measure what fluorescence.
For fluorescence, yes, thank you, son. I stand corrected again. In fluorescence, it's not the transmitted beam that is measured. In fluorescence is the light that is transmitted, or not transmitted, that is produced by the molecule as it relaxes from excited state to ground state. That is very correct. Somebody needs to go somewhere. Okay, so that is absolutely right. I'll show you the image of the last slide of the lecture is the image that shows for fluorescence specifically how the angles in the spectrophotometer or the one that measures fluorescence is angled so that it's not the transmitted light, but it is the fluorescence that is measured. So good, I stand corrected again. In absorption, the transmitted beam is the signal measure. Yeah,
Just to clarify point again, is the transmitted beam that is measured in
yeah, we convert the transmission to absorption because it's negative absorption is negative log transmission.
sometimes the machine does it.
Yeah, not sometimes, all the time. We don't do the calculations ourselves. Yeah, the software does it for us. Yes,
So it's only A for this one?
it depends on the circumstances. Yeah, so, yeah, in this case, if I'm asking about absorption and fluorescence, then B is incorrect. And if I'm asking about quantification and qualitative identification, then C will not be correct. So in an exam or quiz, I'll make it very, very clear. Yeah. Okay, so the range of wavelength for the visible range is usually between 400 to 750, 800. That's the range for visible. And then the range for UV is 200 to 400 nanometer. So that is kind of where the spectra is for UV visible spectroscopy. We can measure absorption and fluorescence in that range. We can do qualitative and quantitative. In qualitative, we're basically looking for identification using spectroscopy or the spectra generated to identify compound or to determine presence or absence, just qualitative. But when we want to actually measure concentration, then that's quantitative, and we can do that as well if we have the proper standards. So sometimes when we're doing qualitative or quantitative, we have inherent signal. By inherent signal, what I mean is that the molecule compound that we are looking at, it can absorb light inherently. It has that, it's a chromophore. So it can absorb light. And for fluorescence to happen, absorption is a must, okay? But measuring absorption does not necessitate that you always have fluorescence. So basically inherent characteristics. So the compound that we're measuring or the atom that we're measuring has the ability to absorb light. So that would be inherent signal. But sometimes the compound that we're after is not inherently a chromophore. That means it does not absorb light inherently. So we do chemical modification to generate a compound that absorbs light and relate that compound to the original concentration. A good example is in glucose measurement. Glucose does not absorb light, but if we react with a particular reagent, it will give me a compound that absorbs light, then I can relate absorption to concentration. So a chemically induced product that we can stoichiometrically relate to the concentration of the compound of interest. So you'll see us applying a spectroscopy for quantification of macrocomponents. So there will be a lab on total carbohydrate where we react total carbohydrate with sulfuric acid to break down the bonds, and then a phenol reagent to generate a compound of color or a chromophore. We will do that in total carbohydrate. And then a quantification of microcomponents. We'll talk about a lot of these microcomponents, but an example is thiamine fluorometric method. We'll talk about it under vitamins. And here we're measuring the fluorescence of the vitamin. Enzyme-linked aminoacids, this will come in chapter when we talk about immunoassay in analysis. And here we have enzymes linked to antibodies or an antigen, and the enzyme converts substrate to a product that we measure absorption of. And that will allow us to determine, for example, allergens, quantification or detection of allergens. So here's a clearer picture of what happens. You have your sample usually in a cuvette. And then you have the incident beam, we refer to it as P0 for incident beam. And then absorption happens, and then the exit beam is the one that continues in case of absorption to the spectrophotometer. So always your incident beam is greater than your exit beam if absorption happens. But again, you have to remember that not everything that this minus this does not equal absorption. There's another image I'll show later which shows scattering of light, reflection of light, potentially some fluorescence generated. So what's important here also is these letters. So C for concentration, A for absorptivity, B is the distance or the length of your cuvette, the sample hole. So relative transmittance or absorption is correlated to analyte concentration, but relative transmission is not linearly related to concentration. Absorption is linearly related to concentration, and we like linear relationship. It's easy to work with. So absorption is usually what we measure to quantify. So you don't have to memorize the equations, but just know that we can measure transmittance by the ratio of the exit beam over incident beam. That's percent transmission is basically multiplied by 100. Like I said, what you want to know and remember, it's not linear with concentration, and that the fraction of the incident beam that is not transmitted does not equal the solution's absorption. So this is what you want to remember. You also want to remember that there is a relationship between absorption and transmission, and it's negative log transmission. This relationship is linear with the concentration, and that's where Beer's law comes into effect when we quantifying this is the relationship. So this is absorption equal absorptivity, which is specific for the analyte, multiplied by the distance of your sample holder times the concentration. This is an equation you want to remember. So concentration can be in any of these forms, can be molarity, can be milligrams per milliliter, parts per million, percentage. So it really doesn't matter based on how you prepare your standards, what concentrations of your standard and in what way you prepare them. The path usually is in centimeter, and absorptivity is basically the inverse, the unit of it is inverse centimeter, inverse the concentration. That's why absorption has no unit, because the units cancel. So sometimes you see absorptivity referred to as A, or a unit for molar extinction, which basically it's called molar absorptivity or molar extinction, same thing. When we see the word molar, that means the concentration is in molarity. That's all. So otherwise, if you have different concentration units, you just call it absorptivity. Okay, we said absorptivity is unique characteristic of the compound. Now, which one of this is correct? Molecular property is dependent on the molecular property of the species. It's dependent on the wavelength at which we're making the measurement. It's dependent on chemical environment. So A is correct. What else? Go ahead, Caitlin. I would say too, it's all of the above. So again, you have to remember Beer's law. To apply Beer's law for quantification, you measure at a singular wavelength. And the absorptivity of the molecule changes at different wavelengths. You have different intensity of absorption that can happen at different wavelengths. You want to remember the UV spectra that happens. You have high absorption at a particular wavelength, lower absorption at another wavelength, and so on. So at different wavelengths, you have different absorptivity. Chemical environment. Chemical environment can indicate pH, for example, or concentration. So if you have high concentration, you deviate, you have intermolecular interactions. If you have anything in the system that cause formation of ions, dissociation, association of protons, you will have changes in the absorptivity. Also, if you have a pH shift, you will also have differences in absorptivity. So usually your environmental conditions need to be controlled. Sometimes we have to do measurements under buffered conditions, for example, so that nothing is changed during the analysis time, so that we don't deviate or have the absorptivity differ. Okay. Valerie?
Sorry, was the example of the pH, does that have to do with the chemical environment or the molecular properties?
Chemical environment which impact molecular properties. Yeah. So the chemical environment is you change the pH, that's going to change the association dissociation state of your molecule. So it's interrelated. Good question. Oh, no, we're passing. All right. So here's the figure or image that shows you that light doesn't really only get absorbed. So you have absorption happening, you have light scattering happening, you have reflection. There could also be some fluorescence. So the difference is not equal absorption. Sometimes to avoid error, not sometimes, always, you have something we call a reference cell. So in a spectrophotometer that only have one place for your cuvette or test tube, usually you run the blank first, you measure them, you put the blank and you hit 0. So you're basically correcting for anything that absorbs or scatter light or fluoresce that could be in the sample other than your analyte. So your blank has similar consistency to your sample except your analyte. Similar reagents, for example, and then you use it to hit 0 so that you can correct for any absorption coming from other than your analyte. And sometimes you have a spectrophotometer that include a reference cell and a sample cell. So you always have your blank in there and you measure samples. So it's always automatically adjusting for the blank. And you'll get absorption that took into account the absorption of the blank automatically without having you to take out the blank and put the sample. And over time, you have to 0 again because there's deviation that can happen. So it depends on the spectrophotometer that you have. You may or may not have a constant reference set. We talked about deviation from Beer's law. Usually, you don't want really to work with high concentrations. For example, over 10 millimolar, you get intermolecular interactions, chemical processes, ionization, dissociation, association, change in pH during a chemical reaction. So that will impact Beer's law. And polychromatic light. So that means if you have multiple wavelengths reaching the sample and then reaching the detector, you don't obey Beer's law in this case because you have multiple absorptivities. So that's why it's very important to have a monochromatic light so that the Beer's law equation is obeyed, where you have a singular absorptivity in your equation. Another important piece is sample preparation. In absorption, when you're measuring absorption, if you have a turbid sample, like in cloudy, like you have your sample and it's cloudy, that means you have large particles in there. So what happens is a lot of scattering of light happens. So then you reduce sensitivity because most of the light is scattered rather than absorbed, and you have much less transmitted light. So the detection limit sensitivity would be not good. So what we often do is we have a clarification step. So if our sample is not clear, we have a centrifugation step where we sediment large particles and we measure absorption of the supernatant, and you would hope that your molecule is in the supernatant soluble. So in sample preparation, we make sure we have the correct control for the reference cell or correct blanks. We make sure that we have the same reagents in the blend that are in the sample. Another thing we have to account for is the cuvette type or the sample holder. So we cannot use glass for UV absorption because glass absorbs UV. So if we have a UV range, we have to use quartz or fused silica for absorption. And quartz is expensive, but it is great to use for UV. When we're measuring in the visible range, we can use glass or plastic. This does not absorb in the UV range, but they absorb in the visible range. They absorb in the UV range, but they don't absorb in the visible range. So we can use glass and plastic for visible. The other thing is we want to make sure that our cuvette has enough sample that allows the beam to go through the sample. If we don't have enough sample, the beam where you put your cuvette might go above the sample. So we want to make sure that the cuvette is filled in such a way that the beam goes through the sample, not above it. So sometimes we don't have a lot of sample. So we use a different type of cuvettes that would raise the height of the sample, even if you have a little bit of sample. Yes, Sad.
Can you use the quartz and the silica for?
You could, but the thing is, you don't want to use them often because they're more expensive. So you save them if you can use glass and plastic. Good question. Yes, Sandy.
Can you clarify for black and black?
For visible range, yeah, because they don't absorb in the visible range, but they absorb light in the UV range. So that's why we don't use them for UV. Okay. Again, selecting the appropriate wavelength is important to maximize sensitivity. So we usually use lambda max, where we have maximum absorption. We use the wavelength where we have maximum absorption, unless we have interference, unless there is another compound that gets absorbed or absorb light at that wavelength. We try to get another wavelength where an interfering substance does not absorb, so we can get quantification. We might have less sensitivity, but at least we can for sure be measuring the compound of interest. So we want to make sure that we have adherence to Beer's law. So here is something we call bandwidth, and this has to do with the slit in the monochromator. So when you select your wavelength, you can actually increase the slit, so you have more radiant power getting to your sample, and you can enhance sensitivity. You can increase that slit if you have absorption. Let's say this is maximum at 313, but let's say at 310 and 314, they're all here. So you get similar absorptivity at like between 312 and 314, let's say. So you can increase the bandwidth, even though you have multiple wavelengths that can go through, you're increasing the intensity of light. So you can enhance sensitivity without jeopardizing Beer's law. Does that make sense? Because if you have the same absorptivity at multiple wavelengths that are close to each other, you can increase the bandwidth, then more radiant power can get to your sample, then you can get higher sensitivity at lower concentration. We often calibrate the instrument before we block the source of light, and so that we have zero transmittance, and we tell the instrument this is zero transmittance. And then we unblock the source of light. There's no sample cuvette, nothing in there. And we tell the instrument this is 100% transmittance. So making sure we calibrate is important before we use our spectrophotometer.
I had a question about that. What is the optimum degree?
It depends on the absorptivity of your molecule. If you know that your molecule really has maximum absorption and very, very narrow at one wavelength, then you have to be as short as possible. But if you know that you have very similar absorptivity over a few wavelengths, then you can increase the length. Okay. So making sure you have linear relationship, and that's why you always, for every compound, you need to find the linear range, the concentration where your line is linear. You want to avoid concentrations where at certain concentration you start having molecular interactions, and then the absorptivity changes, so the line plateaus. So you want to avoid 7.5 in this case and 10. These can be two different compounds. Okay, so two different compounds, even at the same concentration, they will interact with each other differently. So you want to find the linear range for any particular compound, so that then you can dilute your sample to fit within that linear range. You don't want to be measuring under the lowest concentration, and you don't want to be measuring under the highest concentration. So if your sample reads higher than 10, you can't trust that this is within the linear curve. You have to dilute and make sure your sample fits in the middle or somewhere here. So that's very important to consider, and every molecule is different. Okay, this is a little bit complicated. I will not spend a lot of time here, but I just want to emphasize one particular thing. Is sometimes you cannot generate a blank that is exactly similar to your sample. In your sample, there might be so many different components that can cause interference. So if you prepare your standards and blank in different solution, in water or in acid or whatever, it's not going to be the exact same as in your complex sample. And we run into this problem a lot. So we do something called a standard addition protocol. So very briefly, what does it mean, standard addition protocol? Is that you prepare your standards, okay? So you have here your, well, not necessarily standard, your volumetric flask that you're going to prepare your standards and sample in it. So let's say you're preparing you want to generate a standard curve with 4 concentrations. So you have your standard solution here, standard solution. And then here you add to each flask, you add same volume of your sample, unknown sample. U for unknown. Okay, that's just instead of S, use U, similar to what's there. So volume of your unknown sample, the same volume. And then what you do is you take from here different volumes of the standards. Volume standard 3, volume standard 4. Okay, so from the same stock solution of your standard, you just take different volumes. Let's say 10 microliter, 20, 30, 40. Then you're generating different concentrations of standards in each of these flasks, and then you make up to 10 ml or whatever it is, 50 ml, 100 ml. you make up to the same volume. So you have the same total volume. So now you have the same total volume. You know the volume of the standard. You can determine the volume of the concentration of the standard in each one because you know the concentration here, fixed. So you can tell the concentration of standard in each one of those. Fixed. And then you have the total volume, you know the volume of the sample that you added to all of them. Then you plot your standard curve with volume of the standard over absorption. And then you get an equation that you can have all of these. You have the volume of the standard, you have the concentration of the standard, you have the volume of the unknown. You don't have the concentration of the unknown, but you have total volume. So from the equation of the line, you have everything. You have the slope where you can get the constant. You have everything, and then you solve for concentration. So basically what I want you to remember is that when you have a sample that is very complex and has a lot of interfering substances, you can build the standard curve within the sample, okay? And that's how you build your standard curve. I won't ask you to calculate using this equation. I just want you to know that this method exists for future reference. There's a lot of detail in that chapter of your textbook if you need to use that method later in the future. Instrumental error, or otherwise known as noise. Every instrument has noise, and you want that noise to be relatively very small compared to your variation in your sample preparation, in the variation of the concentration among your samples. So you want to have minimal interference of instrument noise. So we want it to be very small. We can test with repeated measurement of a single sample, so we can determine the noise by measuring the same sample multiple times. So you can say, okay, this time I measured it, the absorption was 0.12. The next time I measured it, the absorption was 0.13. The next time I measured it, the absorption was 0.10. Then I know that the noise is about 0.01. Kind of like that. Can be reduced by the use of intermediate concentration. Usually, rule of thumb, they tell you dilute your sample so that your absorption is within 0.2 to 0.8. If you have absorption of 1.5, that's really high. You might have potentially high noise, so you want to lower the concentration where your absorption is between 0.2 to 0.8. That's kind of the range that is recommended. Okay, so monochromator, we talked about that before. So in monochromator, you have the source of light, either tungsten for visible, deuterium for UV. Then you go through the monochromator, where basically you select for a particular wavelength. So the light goes in here, there's a mirror, goes to the grating system. Actually, light goes in here, mirror, goes to the grating system, and you get your light wavelength diffracted into multiple wavelengths, and then you control the bandwidth, allowing for a singular wavelength or close to a singular wavelength to get onto your sample. Then you have the singular wavelength going into your sample. Some of the light gets absorbed, some scattered, some reflected, some fluoresced, and the transmitted light gets to the detector. And you can have a phototube detector or a photomultiplier detector. Phototube detector, you have the light beam hitting a cathode, an electron is emitted and hits an anode, electrical signal is generated and converted to absorption. This photomultiplier tube is similar to the atomic absorption spectroscopy unit that we have, where you amplify the signal. So there are multiple anodes or dinodes, where an electron hits another dynode, gets multiplied into multiple electrons, and this happens multiple times. So one electron eventually becomes 7 electrons, so you amplify, enhance your threshold, enhance your sensitivity using the photomultiplier. Okay, so I will stop here and continue with this on Friday. See you guys. Oh, I haven't finished
Okay, so.
until you revisit stuff.
Okay.
Change their mind?
Just a second. And I want to stop recording.